Having laid the groundwork for elementary motion and talked about displacement, velocity, time, and vectors, we can move into talking about a more realistic motion, and that's motion in 2 dimensions, and specifically the case of projectile motion. So when we're talking about 2D motion, we can look at a situation where the vectors can be analysed in 2 dimensions, and they will of course have 2 components compared to the single-termed 1-dimensional vector. So a 2-dimensional position vector will have components in the x and y or I and j directions. So here is your position vector, here is your displacement vector. So in terms of our vectors, a displacement in the x and y axes will give a displacement vector s, which will equal delta r. This delta r will be a motion in both the x and y axes, or I, j axes. And remember, this is PowerPoint, so the little hats are missing from the i's and j's. This means if we conduct an analysis of the motion, specifically an analysis of a displacement or velocity function, then our 2D velocity vector will be delta r by delta t, or dr by dt, which of course will be a velocity in both components x and y. That means if we want to calculate the total velocity, the magnitude of the velocity of our particle, we will have to employ our Pythagorean theorem and say that v is equal to the root of v squared x squared plus vy squared, as we've seen with our vector calculus and vector notation. So let's talk about 2D motion in a little more detail, and specifically the effects of motion. One of the things to account for is definitely relative velocity. Now this can occur in any number of dimensions, 1, 2 or 3, and we're not talking about relativity here, which is an entirely different thing and makes our velocities even more complex. We'll restrict ourselves to the classical cases. So if you are standing next to a road, vehicles appear to pass by very, very quickly. Now, at the same case, if you are in a car parallel to another car and moving with similar speed, then that car is stationary relative to you, even though both of your reference frames are moving. So from the road side, you'll have what's called a relative velocity. Say the car is moving 35 meters per second. So you'll have a relative velocity from a stationary perspective of 35 meters per second. If you're in a car parallel to the other car, your relative velocity is 0 meters per second, even though both vehicles are traveling. And of course, this is the kind of thing you can see in this kind of processional NASCAR type racing, when 2 cars are parallel to one another and moving at the same speed. The relative velocity between these 2 cars will be 0. The relative velocity to the people in the stands will be a very high rate of speed. So when we talk about relative velocity, we have to talk about our reference frame. Our reference frame is the frame of reference of the individual. Where are you standing? What does a speed or displacement look like from where you are standing? So motion really depends on the velocity of the observer, and it's relative to your frame of reference. So the velocity of the observer has to be accounted for in all of your calculations. So taking a look at this situation, from our frame of reference, this man is moving at 2 meters per second. And even though he's still walking, he's still standing still at this point. Take the same man. Now he's walking at 2 meters per second still, as per our previous case, but he's standing on the back of a truck bed, moving at 4 meters per second, a decidedly unsafe maneuver. Now what does this mean for us standing on the roadside watching him? Again, truck moves 4 meters per second, he moves at 2. This means the velocity of the man on the truck in his reference frame is 2 meters per second. The velocity of the truck relative to the ground is 4 meters per second. Consequently, the velocity of the man relative to the ground becomes 6 meters per second. So if you were watching this situation, you would see him move at 6 meters per second. This is relatively obvious in terms of a calculation, but you do have to make sure when you start a problem that you are in the correct reference frame to solve that problem. And that usually means reading the problem carefully and understanding what it's asking you to do. Now in this case, the man is now moving to the rear of the truck at negative 2 meters per second, with the truck moving still at 4 meters per second. So once again, velocity of the man to the truck is 2 meters per second, but now he's going in a negative direction. So you will experience him essentially moving at 2 meters per second in the opposite direction. A more normal but less animated version of this problem is usually presented in this fashion. Here we have a person walking towards the front of a train. Passengers will see him moving at 2 meters per second. That's people on the train see him move at 2 meters per second. Their relative frame is that of the train. The train is moving at 9 meters per second relative to this man over here that's so very well dressed. The observer, this man in the orange shirt, will see the man moving at 9 plus 2, which will give us 11 meters per second in total. So that's just the idea of what's your reference frames. If you're asked to solve a problem, are you in a stationary reference frame relative to the situation, or are you moving with the situation of interest? Now, as promised at the beginning of this class, we're talking about 2D motion. So, when we're dealing with 2D motion, it's just a little more complex, but not a lot. So in this particular case, this is the same scenario of the man on the truck bed, but now, instead of moving towards the front or rear of this particular truck, he's moving at an angle across the truck. If this were the case, there would be two components to his motion. There would be essentially the velocity of the truck in the forwards direction, 4 meters per second, and then we'd have to look at the velocity of the man and essentially find the resultant of the man's velocity and the truck's velocity, a vector sum of his motion. So let's take a look at an example at this point. Here we have a plane leaving its base, flying at 110 meters per second for a destination 300 kilometers east. The plane encounters a wind blowing 15 meters per second due south. What will be the plane's velocity relative to the ground? Now, it's been said that planes don't actually behave like this, but that's true because they're actually made out of very aerodynamic materials and shaped to be aerodynamic. We, however, are dealing it as this big slab-sided thing that we're just using as an example to calculate our vectors. So, what do we have to deal with? The plane leaves its base at flying at 110 meters per second, 300 kilometers east, and we've got a wind blowing at 15 meters per second due south. We want the plane's relative velocity to the ground. So just for perspective and continuity, here's the guy walking around on the truck bed here on the road going towards this barn for some reason. But here's our situation in general. Here's our plane, here played by a World War II Spitfire, north and east. The plane will end up moving along this direction. The reason being that the plane's speed is in the easterly direction, but the wind is pushing it in a southerly direction. Let's look at this without all the background in a little more of a scientific fashion. So the plane leaves from this point and then ends up at this point. The plane is traveling in a straight line or wants to travel in a straight line, and the velocity of the wind is pushing the plane to the south. We have the airspeed, we have the distance east, we have the velocity of the wind, and we want to know what's the actual resultant velocity of the plane. Well, we can turn this into our own version of the diagram. Always a good idea to help you comprehend it rather than just looking at my diagrams. And here we have the same thing now, essentially written in virtual chalk. So our vector sum is going to be some sum of the airspeed plus the wind velocity. So we're looking at a combination of those two. You should by now understand that this will be a Pythagorean theorem solution. So the velocity of the plane will end up being velocity of the airspeed plus the wind velocity rooted and squared, 110 squared plus 15 squared rooted out. This is solved in its entirety, giving us 111 meters per second. Now the plane is going to travel at some angle theta, and we can use our basic trig once again to figure out how far off course this plane will be when it gets to its destination. So if we take the inverse tan of 15 over 110, we will end up with 7.765 degrees. That's about 8 degrees off course. Now, that doesn't seem like a lot in general terms, but when you're talking about aircraft navigation, that's miles and miles off course, and in the modern world probably means you're being intercepted by jet fighters and shot down, or being taken to some airbase where you'll be interrogated for quite a while. So as per usual, our equations of motion will always apply. We just looked at the situation of velocity. We could have looked at that in terms of displacement. But in terms of calculating our motion, we always default to our same 4 equations. And remember, these numbers don't actually show any order of priority. They're simply numbers to say that there's 4 equations. And of course, we've practiced these, so you should know which ones you use more and how to rearrange each of them. So we talked about velocity, but when we talk about two-dimensional motion, we're often dealing with an acceleration. So when we deal with a two-dimensional motion, really we're dealing with 2 one-dimensional problems. So every problem that you see can be broken down into its component dimensions and each solved for. And of course, using our trig, we can usually put those dimensions back together as vectors. So when we dealt with our one-dimensional problem of an object moving in the x direction, we had possible 4 equations to choose from. Now we have a possible 8 equations to choose from. The 4 equations of motion in the x direction and the same 4 equations of motion that will describe our motion in the y direction. So the same equations of motion we've always seen here in the x, and we can make the selection in the y based on what we have in the x and what we have in the y. Do we have an acceleration or a velocity in x, or an acceleration, a velocity or time that we see in y? And you do have to solve the problem essentially twice. So if you can do a one-dimensional motion problem, you can usually do it too. Usually the question is, what is the common factor between the x direction and the y direction? Now, when we look at a two-dimensional problem, especially the problem of a parabola, when we actually throw a projectile or launch something, what's usually happening is gravity is pulling it down while you give the object a velocity in the x or forward direction. So usually a here is replaced by g. Now when we deal with acceleration, of course, Acceleration is essentially the change in our velocity, and we can express our velocities and accelerations in terms of unit vectors should we wish to do so. So don't forget the disciplines that we've looked at previously. So when we talk about 2D motion, what we mean is an object travelling in a two-dimensional path. As I say, usually a parabola, and for most of the cases we're dealing with, the object is going to be under the influence of gravity. Let's stay on Earth and deal with gravity of 9.8, unless I say otherwise. So with motion in 2 dimensions, of course, remember, you can create 2 independent one-dimensional motions to solve. So when we deal with a projectile and we talk about a parabola, there's a whole family of different parabolas you could have, essentially, or different behaviors under the action of gravity. Your object could just drop straight down. Your object could be thrown up at a very high angle, creating a very steep curve. Or your object could be thrown at a much longer angle, and your object could end up going in a long parabola. So the ratio of how far your object goes in the x direction, which is referred to as its range, and its altitude or height, the ratio of these two tells you how big your parabola is, or the dimensions of your parabolic motion. Now, the things that really determine the trajectory of your projectile are the initial velocity, the launch angle, which we will always deal with as theta from the horizontal axis, and of course the acceleration due to gravity. And projectiles encompass a lot of different things. The study of projectiles can be applied to many, many different facets of life, from dropping ordnance or anything from the sky onto a specific target, throwing baseballs, of course, rockets launching, specifically ICBMs and space rockets, where you want to make sure they either land on a target or land in an unpopulated place. So let's take a look at a quick question here and ask yourself what's going to happen. Here we have a very comical situation, and believe me, none of the cartoon soldiers in this particular slide were injured during the making of this lecture. So here we have a World War II bomber here with a big bomb on the bottom, and it wants to drop this bomb on this offending tank over here. So the plane is moving from the left to the right with the bomb on the bottom. Gravity, of course, is acting downwards. The question you want to ask yourself is, if this plane continues at a constant velocity and drops the bomb at this point, where will the plane be relative to the bomb when it hits the target? Now, ignore air resistance. We'll talk about air resistance towards the end of this particular class, but just think about this for a moment. The plane has a velocity in the x direction. That's from the left to the right. When it drops this bomb, that bomb will be imparted with the same velocity in the x direction. Now, neglecting air resistance, this bomb will not slow down in the x direction and will continue with the same x velocity as the aircraft. The acceleration due to gravity, g, will be acting on this bomb. Consequently, as the aircraft moves from left to right, everyone gets out of the tank, the bomb will land on the tank, moving with the same x velocity as the plane. So the answer is, as long as the bomb and the plane travel with the same velocity in the x direction, the bomb will gain velocity in the downwards direction, giving you a parabolic curve, and it will explode underneath the plane. Now, it's not that I'm that martial or particularly that violent, but when it comes to things like two-dimensional motion and parabolas and looking at trajectories of throwing very heavy things, it tends that it follows the development of weaponry, basically. People for a very long time have wanted to hit other people or other creatures, or if they were hunting or something else, from very far away, right from throwing rocks through to trebuchets and complex catapults, to bows, to firearms and cannons. And all of these things really are excellent examples of two-dimensional motion, of motion of a parabola. And that means we know a lot about the behavior of two-dimensional objects, of projectiles. So, as we just discussed with the aircraft problem, our system was under the influence of gravity and was also, of course, subject to our usual momentum equations and velocity. So, we'll talk about forces in more detail in subsequent sections, but right now, let's just introduce Newton's first laws in their entirety here and just discuss them in a bit more detail. So, Newton has three laws that he came up with, and he also came up with a law of gravitation as well, which we'll discuss later. There's also a law of cooling, which I think is probably my least favourite Newton's law and kind of common sense, but that won't come into this class. So as far as Newton's laws go, Newton's first law makes this statement: an object moves at constant velocity unless a net force acts to change its speed or direction. That means if you leave something alone, it will continue its motion, continue its behavior, either moving in one direction or standing still, until some external force interferes with it. This could be looked on as one of the things controlling the bomb in our previous example. Newton's second law, the only one that has an equation associated with it directly, is F equals ma. This is a force is equal to a mass times an acceleration. So if you have a force, you have to have an acceleration. So in this particular case, this man is throwing this baseball. He's accelerating this baseball because the force is applied by his moving arm. When he lets go of this ball, he is no longer applying a force. So the force from his arm stops, and once he lets go of the ball, the only thing that's modifying the path of that ball is gravity pulling it down, and air resistance, which is acting against it, which we'll come to later. For all the examples I'm going to show here, let's not worry about air resistance right now. And of course, there's Newton's third law, which gets corrupted in all sorts of philosophical ways and mentioned in arthritis commercials all the time. And for every action, there is always an equal and opposite reaction. Now we're going to see this come back to us with a vengeance when we start talking about things like friction. But here, we're going to look at this from the point of view of our two-dimensional motion. So with that reminder, let's take a look at getting back into our motion. So our objectives today are to describe the changes in horizontal and vertical components of our projectile's velocity, which of course means its acceleration as well. Change in its velocity is implicit in acceleration. We'll also explain why projectiles move equal distances horizontally in equal times. We've kind of already done that. These are the things you should be getting from it. And we're going to restrict most of our examples, or all of today's examples, to situations near the Earth's surface. So we will consider the force of gravity to be a constant, a g equals 9.8 meters per second in every single case. So here's a calculation we're going to see in a later class. And if we look at the variation of gravity, we can see that gravity is actually acting even in orbit. If an astronaut is in orbit in a space station or spacecraft, the only reason we turn them weightless is because they're constantly in a state of free fall. It's got nothing to do with the fact that gravity is lower in space. The gravitational attraction and of course the gravitational acceleration will be lower in orbit than it is on the Earth, but not by much. The reduction of gravity in orbit is actually extremely small. So if we're to actually just look at, say, how much our weight changes if we go to the top of what's now, I think, called Willis Tower, until somebody else buys it, we can take a look at how much our weight varies. The tower height here is 400 meters. The radius of the Earth, though, is 6 times 10 to the 6 meters. This means if we go from the bottom of this tower to the top of this tower, the difference in the force of gravity is only 0.01%. That means we don't really need to add that to our calculations today. We're not being that accurate. We're trying to understand how gravity varies rather than go to the nth decimal place with our calculations. So as far as we're concerned, anything on or near the Earth's surface that we'll deal with are under a constant force of gravity. So please don't ever, in this particular segment, say, well, we're looking at a differential in the gravitational force. This is not true. The other thing I want to give as a reminder is this simple fact. And this is something that people usually know, but often violate in calculations and when writing out problems. And this is something that for a long time took a lot of convincing to a lot of people. Now, Galileo didn't actually do this experiment. This was a thought experiment that he wrote down, and I realized that the Tower of Pisa didn't exist in Galileo's day, but we're going to go with this. So, in terms of gravity, here we have two masses, M2 and M1. If you take both of these masses to the top of a tower and you fling them off at the same time, they will both hit the ground at the same time. It doesn't matter if one is 10 tons and the other is 4 pounds. They will still hit the ground at the same time. As I said, we're ignoring air resistance. One of these doesn't have wings, one of these isn't a feather, versus one of these being a cannonball or something like that, which will react differently to convection currents and things like that. Let's just say these are both the same ball and they both react the same to falling through a fluid like the Earth's atmosphere. They will both hit the ground at the same time and land simultaneously. And quite often, people will forget this when they're doing calculations and make a statement that the bigger mass will hit the ground before the smaller one. This is not true. So, when we're looking at these kinds of misconceptions, there was a large-scale survey that was taken, and elementary through university students were asked, if you neglect air resistance, which of the following paths would a ball follow if it rolled off a cliff? Well, would the ball leave the cliff, stop, and then spontaneously travel downwards? Would it move forward at first, but eventually fall straight down? Or C, would the object then continue to move forward for the duration of its fall? We've kind of already answered this question, and please, I hope you are picking C. However, when the survey results were studied, here's our three paths, 60% like A, that the object moves, stops, and then falls straight down. 24% said B was a great option, moving forward and then suddenly starting to move down. And 15%, just 15%, liked C. Please, in this case, be in this minority of 15%. The object will continue to move forward as it falls down. But we're left with this really unfortunate and relatively sad result that 60% of the populace over all ages seem to like the idea that Looney Tune physics was in play here. And this isn't so much that people are stupid, although some people are. This is not the case. People, very smart people, can often have a disconnection between observations and logical models. And this especially happens when you're trying to do a calculation and focus on formulae and focus on other things. It's very easy to make these kinds of statements that you really wouldn't make in normal everyday life. So please be aware of that and be a little careful with that. So let's get back to our calculations. So remember, Our projectile motion is a combination of motion in the x direction and motion in the y direction, horizontal and vertical motion. Now the horizontal motion of a projectile is constant because we have no gravitational force acting horizontally. And as I said, we're going to ignore friction and air resistance in the cases we're going to look at here. So we don't have to worry about variations of velocity in the x direction for our calculations, only in the y direction, only in the vertical case. So let's really study what would happen to a coyote if he ran off a cliff. So we're using real physics here and applying it to cartoons. So if a coyote runs off a cliff, as he leaves the cliff, he will have his horizontal velocity. As soon as the coyote leaves the cliff, he'll experience a vertical force. Now he's always experiencing that vertical force, even though he's on the ground. It's just that it's not having the effect of accelerating him down in the y direction. He's not picking up speed in the y direction because he's in contact with the ground until he leaves the ground. So let's take a look at his actual motion. Here's our coyote over here, and here's the roadrunner that he basically wants to eat. He's going to do this. Boom. Please make the sound effects for yourselves as well. I just like that. So here's our coyote. At the beginning, he's going to start out with a velocity in the x direction at t equals 0. He's going to run off the cliff, and he's going to maintain his velocity in the x direction. Remember, no air resistance, so Vx at t0 is Vx at t1. Now, he's gaining a velocity in the y direction. Gravity is acting down, and it's giving him 9.8 meters per second for every second that he's falling. Now at t2, Vx is the same, but now you can see that his y velocity vector is increasing. He's accelerating downwards. And finally, his Vx is still the same, but his y direction vector, his velocity vector in the y, is significantly increased. This means he's accelerating in the y direction and keeping a constant velocity in the x direction. That will make him move in this parabolic trajectory. And that's the real physics behind the parabolic trajectory for an object moving in 2 dimensions under gravity. So gravity is causing a vertical acceleration, and he's gaining velocity in the vertical direction as he falls, and Vx stays constant. Now I've said that a few times, and it might seem like I'm labouring on this point, but please remember this when doing your calculations. So the vertical motion of any projectile is due to being in free fall with your constant downward acceleration of negative 9.8 meters per second per second. Now, something to remember when you are solving problems, and as we've said, we can do all of our calculations by defining an equation for v, for instance, or s, or even a, in the x direction and in the y direction separately. So essentially 2 equations of motion can be defined for this system, one in the x and one in the y. But those components of motion are distinctly separate from one another. That means that when the coyote moves at t0, he's moving in the Vx, in the x direction. As he goes off the cliff, he now has a Vx and a Vy. You cannot put these 2 axes necessarily together in terms of their behavior. Now we can calculate, of course, a resultant vector which is giving us our parabola, but the velocity in the x direction has absolutely no physical influence on the velocity in the y direction. You cannot mix these 2 axes. And I know some of this sounds a little obvious, but I am pointing out the most common errors that people make. For instance, you cannot take an acceleration in this axis and use it in an equation of motion in this axis. And that is one of the most common errors of people seeing an acceleration, seeing a velocity, and putting them together. You cannot use an acceleration in the y direction with a velocity in the x direction, for instance. So that means that the velocity of the object's motion here in the x direction is the same throughout his motion. The velocity in the y direction is going to get bigger and bigger and bigger with time as the coyote falls. Now, in terms of a less florid, simpler to understand diagram, here a ball goes off of the cliff, and essentially here we are again with our constant velocity vector in the x and our increasing velocity vector in the y direction. Now, we haven't talked about inertia, and it's going to be a while until we talk about inertia, which is essentially the body's resistance to motion. But once the projectile moves off of a cliff, for instance, or going in a two-dimensional motion, it's only the inertia and gravity that will affect it. Gravity accelerates things downwards, but doesn't do anything in the x direction. And there's a relatively simple experiment that's often performed, and this is one where people take a ball and drop it in the vertical direction. At the same time, they fire a ball in the x direction, in the horizontal direction. Now, if you look at this and these balls are fired at exactly the same time, you can add essentially the vectors of the position of the green ball here in the horizontal and the position of the red ball in the vertical, and you can add these two together, and what you'll get is a parabolic motion. Adding Vx here and adding Vy together, or adding Sx and Sy, will give you this curved motion, as if the ball has been thrown in this parabolic trajectory. And this has a very important result, and that's one you need to keep in mind and really convince yourself of. And that means an object that's projected horizontally, that means fired, say, from a cannon in this case, in the x direction, will hit the ground at exactly the same time as an object that's just dropped vertically. Now, people don't like this idea because the object is clearly moving in the x direction while this one is not. But gravity is providing the same acceleration to both of these masses in the y direction. So it doesn't matter if it's traveling in the x direction here, it will still hit the ground at the same time. So that means if she drops this ball at the same time as he fires a cannon, then we will end up with both of these objects hitting the ground at the same time. And this is a concept you really need to consider, and people really need to get their head around. So make sure you're convinced of this particular idea. So just a little bit of terminology before we continue. The path of a projectile is known as its trajectory, and the trajectory of a projectile in free fall is parabolic. The total distance in the x direction that's traveled by the projectile is called its range, and the time it takes to get to its destination is referred to as its time of flight. And we could, of course, look at vectors for each part of this motion. So taking a look at a couple of examples, here we fire a ball, a cannonball, in the x direction. Now, as we can see from the readouts here, the horizontal velocity is constant and the vertical velocity is changing as we've seen before. But here you actually get some numbers to put with this. The velocity of this cannonball as it's fired is 100 meters per second. In the y direction, it's gaining 9.8 meters per second, which is about 10 meters per second-ish. So for every second of travel, it's traveling in the y direction another 10 meters per second faster. And that will give you this parabolic trajectory. So let's take a look at a calculation. By this point, you're probably saying, get to the point, we want to look at a calculation. So let's do that. When we're dealing with something like a rifle, this is obviously a device which is going to project a projectile forwards at very high rates of speed. Traditionally, people who look to calibrate firearms and to calculate things to do with firearms tend to use yards, and you'll often see things quoted in yards and inches. We're going to restrict ourselves to meters per second, but here we're talking about an actual graph taken from a real data set which was given in inches and yards, and you can see the parabolic trajectory here based on the elevation of the rifle and how far it has traveled. So this is often a time of flight experiment as to how far a bullet or projectile will travel. So in the cases we're looking at, if we fire a bullet straight forwards, it's never going to rise above the barrel. Don't worry about the barrel jumping up due to recoil. It'll come out dead horizontally and then start to fall below the height of the barrel and descend at the moment it leaves the barrel. So for a situation like this, our equations of motion are perfectly put together to explain them. We just need to look in 2 dimensions. So remember, write down these equations of motion as we go through these examples and have them handy, just so you can glance at them and figure out what you have through our shopping list method and what you want to calculate. So let's look at the drop of a rifle bullet. So we take a bullet and we put it into a rifle and we fire it completely horizontally directly at the center of a target. We're assuming we're perfect marksmen here. The bullet exits the gun at 890 meters per second. The bullet will strike the target 0.017 meters below the center of the target. The question is, what is the horizontal distance from the gun to the target? i.e., what is the range of this target? So let's turn this into one of our handy diagrams once again and look at our situation. Here's our rifle, not to scale of course. Here's our target. The bullet fires from the gun. I realize that the bullet would not look like this, but we're trying to make it visible. The bullet fires from the gun and then drops under gravity as it moves, causing the bullet to strike below the center of the target. So here we're looking at the range, delta x, how far in the x-axis has this bullet traveled, and delta y, how far has it dropped. So you only really have 2 variables in this particular formula, delta x and delta y. So we know that the bullet will drop at 9.8 meters per second. So for every second of flight, the bullet will be dropping in the vertical direction by an extra 9.8 meters per second. Now, if we're to look for some commonality between our x and y directions, this is nearly always found by the time of flight. So let's just go back 1 second here and just think about what has to happen here in this physical situation and what could be the same in both of our equations in the x and y axes. Now we have a gravitational acceleration that we just talked about in the y-axis that's not present in the x. We'll have a velocity in the x that isn't present in the y direction, as all the velocity is in the x direction at the beginning of our problem. The only common thing between our equation that we'll set up in the x and our equation we will set up in the y is time. The time it takes the bullet to cross the distance delta t is the exact same time it will take it to drop by 0.017 meters in the y direction. And that will be the same for both. T is common between our 2 axes. So finding t, we can solve either one of our problems. So S We don't know delta x, but we do know how far the bullet dropped, and that would be easy to measure. So S is going to be a drop in the y direction, delta y. And this is going to be VIT plus half AT squared as the equation we're going to select. Now in the y direction, you nearly always can select an equation that utilizes A, because you're in the direction of gravitational attraction. I've reversed this equation and put VI and T at the end because, in our case, the bullet starts out from inside the chamber of the rifle at a velocity of 0. So as the bullet exits the rifle barrel, its velocity in the y direction will be 0. It will only start to gain velocity in the y direction as it travels between the rifle and the target. So we can safely say the VIY is 0, giving us half AT squared, or more accurately, half GT squared. So T will be 2y over g. So our time will be twice the displacement divided by the acceleration rooted if we rearrange this equation. That will give us 0.059 seconds. Now, where people often go wrong in this particular problem is trying to look for one all-encompassing equation that will solve this problem, and that cannot be done. We just looked at the y direction here and calculated t. That t applies to the y direction, the drop of the bullet, but also applies to the distance traveled in the x direction. So now we can take t and we can solve in the x direction. So you nearly always have to look at one axis, determine a variable, and then find another equation to explain what's going on in the other axis of interest. So here we calculated t in the y direction. T for the y direction is t for the x, and now you can do one of two things. You can go back to your equations of motion. You can study them, decide which equation you want to use, and attempt to employ one. And that will work. But what do we have? We want delta x, and we've got t. We can use just outright speed is distance over time, or velocity is displacement over time. We know the velocity of the bullet is 890 meters per second. So rearranging, we can say s in the x direction is v times t. So delta x in our particular problem becomes 52.4 meters. So take a look at this particular problem and think about how to solve it using the equations in the y direction, because we have the drop and we have acceleration, to solve for t, then substituting t into an equation in the x direction. In this case, a relatively simple equation of distance over time being rearranged. Now, where is this useful, you might ask? Well, as a physics professor sitting at your desk minding your own business, trying to get your work done, you obviously don't think that someone is going to randomly give you a call and say, hey, someone's been shot in the local baseball stadium, and we would really like to know if someone was shooting at the stadium or whether this was an accident due to a gun battle a mile away. So, not wanting to be accosted by the local CSI and told that I don't know what I'm talking about, I attempted to put together this whole thing. So the local radio station asked me this question when I was living in St. Louis, and I wasn't expecting this call. So grabbing a piece of paper and starting to do some basic calculations, armed with where the woman was sitting and how she was hit by the bullet, I attempted to explain this particular situation. Now, initially thinking that the woman was killed, I was actually incorrect. It turned out she ended up with a bit of a scratch on her hand, so that enabled me to immediately decide that this bullet did not have a lot of energy. Assuming the bullet was then 9mm, a very common caliber in this country, and that basically, you could look up the exit velocity, the muzzle velocity of that particular bullet. You can do some basic calculations and look at the trajectory both from a mile away and right outside the stadium walls. Now, one of the things that you have to do when you're dealing with the press is kind of be very explicit, but then they still misquote you. Now, from the calculation, I would say that the bullet definitely would make it over one of the stadium's walls if it was fired from right outside. It's also possible from the gun battle going on 1 mile away that the bullet could also make it over the wall. Now, in my opinion, the bullet probably bounced off of the roof of the stadium and then struck her, hence the fact it didn't have a lot of energy and was probably at the end of its travel. They did get that bit right in my quote. I did not say that it was fired almost straight up necessarily. I really don't think someone was shooting from outside the walls. My calculations, based on just a few minutes of work that I had to do, really showed that this bullet was probably fired a mile away at a relatively high angle, meaning someone had a firearm and was a very bad aim. So speaking of which, let's take a look at another problem involving the trajectory of a projectile. Now, this particular problem used to involve a monkey falling from a tree. People didn't like the fact the monkey was being shot at, even though it was a tranquilizer dart. So I changed it from a monkey to a predator, because apparently we don't mind extraterrestrials being fired at. So in this particular case, you've got Arnie walking through the jungle attempting to get to his chopper. He sees the predator hiding in a tree, then aims and fires his weapon at the predator. He's firing at the predator because it's probably end up skinning him and pulling his skull off, so it's quite acceptable. So he fires at the predator hiding in a tree, and at the exact moment that the bullet exits his gun, the predator lets go of the branch and drops straight down. Doesn't jump in the air, just drops from the branch. Now here's the question you need to ask yourself. How should Arnie here aim to make sure he hits the predator? Now please excuse the rate of fire in the next slide. It's a bit of a liberty to make the slide interesting, because that way he could just shoot the tree down. But let's say that he's firing straight forwards here. How should he aim to hit this predator? He's going to fire his weapon, and the predator is going to drop straight out of the tree. So the question is, how should he aim to make sure he hits the predator? Does he aim straight at it? Does he aim high over its head? Or does he aim low, below the predator, in order to hit it? So stop and think about that for a moment. Which of those options do you want to employ? Aiming at, aiming over, aiming below. So let's analyze our situation a little bit. The predator is over here in a tree. He's down here with his foot on a rock, attempting to fire at it. Should he aim that way, straight at it, over it, or under it? Well, remember, what do we have to work with? Always look at what you have to work with. And he has a gravitational attraction to the Earth of 9.8 meters per second that's going to act on his bullet. There's the distance here from him to the predator in the tree. The predator is going to drop from the tree at the same time as the bullet exits the gun. There's going to be an X direction, a range, an angle theta for his bullet, and of course a height, a delta Y, through which the predator will drop. We want the bullet to intersect the position of the predator. So it's not like we're trying to make the bullet zoom across here and essentially hit him here. We want the bullet and the predator to be in the same place at the same time in order to hit it. So what we need is the bullet to traverse delta X in the same time that the predator drops delta Y. And as we've seen before with some of our other explanations, this is something that we can definitely do. So if your decision is made, whichever of the three, the answer will be aim at the predator. If the bullet leaves the muzzle of the gun at the exact moment that the predator drops from the tree, the bullet will drop at 9.8 meters per second, and the predator will drop at 9.8 meters per second. This means that the bullet and the predator will intersect right below the tree, as the bullet will follow a parabolic arc, and it will essentially prevent Arnie from being killed by the predator. So, you may not be entirely convinced. Let's take a look at this problem. So remember, here we're firing at the predator that's sitting in the tree, distance h, or delta y here, vertically above him, and a distance r away horizontally. He fires straight at the predator. Just as he fires, the predator drops vertically straight down. And the question is here, does the bullet actually hit him? Well, we just said it does. So here's our proof of this particular fact. And if you're calculating this question, you should, of course, draw yourself your own scruffy diagram. The version here is obviously better than my artistic attempt right here. But this is informative to me, and as long as these things are informative to you to solve the problem, that's all we need. So remember, just as a general rule, gravity has no horizontal effect on the velocity in the x direction whatsoever. So we need to set up our equations in velocity and time and consider directions of the velocities that are in play here. I would definitely say first consider the predator and then consider the bullet. Either way, doesn't matter which order you do it in. But for the predator, here we have a velocity that's initial VI of 0 as he's sitting in the tree, and its velocity in the horizontal direction is essentially 0. So he's not moving in the horizontal direction at all. He's going to drop in the y direction. This means that his displacement is going to be whatever height he starts out at, plus s equals VIT plus half AT squared here. Don't worry, the signs will work themselves out. Now we said VIT was 0 once again, and you can see the similarities to the bullet drop problem here. So S is 0 plus 1/2 negative GT squared plus H. This will give us his height minus 1/2 GT squared. Well, we know that G is negative 9.8. Now let's make some definitions for the bullet. The velocity in the horizontal direction here is just not an outright velocity. The bullet is fired upwards at an angle. That means the x component, the horizontal component of the velocity, has to be taken into account, which is Vx, which is v cos theta. The vertical case, Vy, will be v sine theta, and we know acceleration is negative g. Once again, taking into account VIT plus half AT squared, we can substitute in here for our initial velocity. So we find that the displacement in the y direction is v sine theta minus half gt squared. Now this should be similar to our order of operations that we looked at for the bullet drop, remember. So in order for the bullet to hit the predator, they have to intersect directly below the predator's position. So let's set the vertical position of the predator and the bullet equal to one another. By doing so, we're creating a solution for a scenario where the bullet hits the predator. And this is very much the same kind of solution you'll find for, say, firing solutions for submarines and torpedoes, or Patriot missiles taking out ICBMs and Scuds. So we set the vertical position of the predator and the bullet equal to one another. So v sine theta t here minus 1/2 gt squared will equal minus half gt squared. So we're setting these positions equal. This will simplify down, as we have half gt squared on both sides, to v sine theta t is equal to h. Now we can use the fact that r is equal to v cos theta in the x direction here. So v cos theta equals r. Now we have two equations. We have the height here, we have our equation in the y direction and our equation in the x direction. Now, in order to find the final position here, we can look at these as proportions. How far did the bullet essentially drop and predator drop here, and how far did the bullet travel in the x direction? So we can divide 2 by 3. So if dividing equation 2 by equation 3, we end up with v sine theta t over v cos theta t, which will give us h over r essentially. This will cancel out our velocities, giving us sine over cos is equal to h over r. This should be pretty much the most basic trig identity you should know. So sine theta over cos theta equals h over r reduces down to tan theta equals h over r. So v and t both cancel. The velocity and the time cancel out here, and all that really matters is the launch angle of the bullet, because the launch angle dictates the height and the range of our bullet. So v and t both cancel, so he will always hit the predator if he aims straight at it. Now I realise there's a lot of technicalities here, a lot of things that have to be abided by. Now he will always hit the predator if he aims straight at it and his bullet leaves the barrel of the gun at the same moment the predator drops, which, given the rate of fire in our animation, is probably quite likely. There is an alternate version of this particular treatment. It's faster and a little dirtier, but it's still valid. And this takes into account the fact that the predator starts a vertical distance again of h above Arnie and a distance d away, and we can break this immediately into x and y components. The horizontal position of the bullet will be v times t in the x direction. So that means t will be d over v, the distance travelled over the velocity. The vertical position of the bullet is going to be vt minus half gt squared, as we determined before, which gives, if we sub in for t from this equation, this will give us the y position of the bullet, the height of the bullet, will be dv over vx, essentially minus half gt squared. We can compare that then to the vertical position of the predator, which will be half minus gt squared, and that means if Arnie aims right at the predator, tan theta will end up being h over d, or vy over vx. So dvy by vx will be height. So when the bullets travel the distance d horizontally, the vertical position will be this. So you can aim right at him. Again, this is just an alternate treatment. It's not quite as rigorous as the first treatment, but it's still just as valid. And if this was an exam or assignment, I would accept either reasoning. So what we should have seen for our vertically launched projectile here is that gravity is always acting on our system. So if we fire something upwards with a y velocity and an x velocity here the x velocity is unchanged. The cannonball is fired from this cannon at 60 meters per second in the x direction. In the y direction, however, its velocity initially is 60 meters per second as per the x direction, but due to gravity, the y velocity will eventually reach 0. As the cannonball travels upwards, its velocity will diminish as negative 9.8 meters per second acts on the cannonball, taking it to a turning point, a 0, and then it will fall down. Now, a really useful part of this, of course, is when the cannonball reaches ground level again, it will be traveling downwards at the same velocity that it was initially traveling upwards. So its starting and ending velocity at ground level should be the same. And we can see that from this readout here. Here the velocity in the y direction, 60 constant for x, will vary. So we fire in the y direction, 60 meters per second, 0 at the top of travel, and then 60 meters per second when it reaches the same height as the cannon. If it continues to fall, as in this example, then it can exceed the 60 meters per second it was initially fired with. Here's the same situation, just shown as a static case, so you can see the vectors. Here's the initial firing of the cannonball. We can see that this is our resultant vector. We have velocities in the x and the y. The velocity in the y direction is diminishing, eventually reaching that stationary point at maximum altitude of 0. As it turns around and comes back down, it gains all of the velocity that it previously lost in the y direction, meaning when this object reaches the same altitude it was launched from, its y velocity is the same as it was when it was launched, just in the opposite direction. Vx remains unchanged. So we've said it many times. In all of our problems, assume a constant Vx, a constant velocity in the x direction. Assuming acceleration due to gravity is only in the y and is always negative 9.8 meters per second. So in our unit vector terms, we'll have AI plus AJ will be equal to negative GJ. So if projectiles are launched at the same speed, but at different angles, we can see that the height and the range, and the proportions of the height and the range, will be affected. So take this cannon, fire it at 15 degrees, and we'll see the shallow parabolic arc. Fire the same cannonball now at 30 degrees. We see we have both an increase in range and an increase in height. As we reach 45 degrees, we can see again increase in range and height. Now once we exceed the 45 degree limit, so let's go to 60 now, we can see that we're gaining height on our trajectory, so our parabola now is higher in the y direction, but is diminished in the x direction. The range is reduced, but the altitude is increased. Going even higher now, at 75 degrees, we can see now that we reach a high altitude, but a small range. Now this will continue as we exceed 45 degrees, and we will end up with greater and greater altitudes and diminished range, until you hit 90 degrees of course, where essentially without any wind or other effects, if you fire this cannonball straight upwards, it should come straight back down and obliterate the cannon that fired it. So the greatest balance of altitude and range for any particular projectile is always 45 degrees. So looking at our situation, the maximum range in the x-axis we can attain is at 45, and the maximum altitude will be at 90 degrees, which of course in this case would be a little bit unwise. So, just as a quick question, which angle of projection causes a projectile to stay in the air longer, 50 or 70 degrees? Well, the higher your object goes, the longer it's in the air for. 90 degrees was our maximum, so consequently 70 degrees will result in our object being elevated and in the air for longer than 50. So remember, when we are looking at firing objects at some angle of theta, we can fire our cannon shell here at some velocity v, and we can always break it down into our components of v sine theta and v cos theta, where theta is the angle from the horizontal. And as we've seen, for this situation, the components of our velocity over the parabolic arc will vary in this fashion. hitting our Vy of 0 at maximum altitude, and then reaching the same velocity at the altitude it was fired as it comes back down. Now, of course, as it hits the ground, Vy and Vx will be 0. And you should always say, well, what velocity does it hit the ground? The velocity it hits the ground at is always the velocity just before it strikes the ground. So in this case, it'll probably strike the ground at a slightly lower altitude than when it was fired, but not much. So essentially, we could say the initial velocity is equal to the final velocity. Be careful in these problems. One of the most common errors is people to set their maximum altitude velocity at 0 and then the velocity at the ground at 0 and end up with 2 zeros and an unsolvable problem. So interpret your questions correctly. Another way to think about this situation is if we take this ball and somebody throws it from one position to another, so essentially from one person to the other, if it takes 8 seconds, which is a bit of an exaggeration but works nicely mathematically, if it takes 8 seconds to be thrown in this parabolic arc and for this person to actually catch it, then it will take 4 seconds to reach maximum altitude. This means that the rise time of any object is equal to its fall time. And this should make sense, as the velocity that's being taken away due to acceleration due to gravity is the velocity that's given back as it falls. And this can often be a little technicality that you need to remember that helps you solve a problem when you don't have t for your parabolic arc. You might have the time it takes an object to go from the start of its travel to the end, but not how long it takes to reach maximum height. So if you have to calculate here in the y direction to the maximum height and you don't have t, you could say this was 8 seconds, half 8 is 4. So as I said, remember this effect. This can be very useful if it looks like you don't have enough variables to solve your problem when you're looking at a parabola. And this is due to the vertical velocity, of course, changing by 9.8 meters per second in the y-axis every second. And it's this kind of parabola that was used in the early days of the US space program. In the early days of the space program here, the Russians launched Sputnik, a vehicle which went into orbit and politically scared everyone, since Sputnik was heavier than Russia's heaviest nuclear weapon. This was not well looked upon, and the American space program was severely accelerated. Unable to have rockets that were equal in power to those of the Russians, the idea was to put a person and in orbit as quickly as possible. So the idea was to put someone in a parabolic trajectory. Parabolic trajectory, that is. And that means to go up in an arc and then come back down without going into orbit. And this is how early spacecraft and early astronauts in the US space program were launched, until the rocket technology caught up with that of Russia and was capable of achieving orbit. So in terms of projectiles, remember, if we are firing a rocket upwards, we'll have our acceleration upwards initially, and we've seen this exact problem before, but now we should be able to completely characterize it. Our rocket will end up with the fuel burning out, will continue upwards until gravitational attraction of 9.8 meters per second downwards has removed all of its velocity. It will hit a velocity of 0, and then we'll come back down to the Earth. So to summarize, and I've said this many times, our horizontal motion should be considered constant. Vx should be considered constant. Vertical motion will have an acceleration. Our rise time will always equal our fall time. And our final speed will equal our initial speed. Now let's just make this situation that little bit more realistic. All the way through, you've probably been tired of hearing me say ignore air resistance, just to make sure people did. But in terms of air resistance, in the real situation, Vx will not be constant. It'll be closer than it will be in the y direction, but you will always have a slight negative acceleration resulting from the fact that your projectile is moving through a fluid. So Vx will be diminished a little bit. For most of the cases that we look at, we can usually ignore this because our object is usually fairly aerodynamic, and this effect is relatively small compared to the velocity change in the y direction. But it is there, and air resistance will impede your forward motion. So if we're looking at the realistic case here, we will end up with a situation where our parabolic trajectory is not quite a truly symmetric parabola. So here's the ideal path. If we fired a projectile from this cannon, it would go in this nice symmetric arc. In reality, it would probably be a little bit shorter. Exaggerated a bit here, but the actual path you would be diminished in terms of altitude and in terms of the range. It turns out that this tends to be just an additive factor, and you can actually calculate all of your particular situations in the cases that we've looked at before, ignoring air resistance, and then simply add the air resistance on at the end of your calculation, or of course subtract it if you were looking at velocities and accelerations. And the resistance that's encountered when an object moves through a fluid is given by this particular formula. The drag here, d, is going to be equal to 1/2 c rho av squared. A is the cross-sectional area of your object. Rho is the fluid density, or the density of air for the situations we've looked at. C, now this is why we haven't put this in here, is a drag coefficient, typically from 0.1, because there's a point there, to 0.4 for most objects. And V is how fast your object is traveling. So velocity does scale your drag factor. The faster you travel, the more higher your drag will go in terms of a squared relationship. This actually gets worse when you start traveling at very, very high speeds, speeds in excess of the speed of sound or approaching the speed of sound. Then it starts scaling as, say, v to the 4. So if we were to look at a vertical fall with drag incorporated, here we've got our body falling under the action of gravity, which would be F, which would be mg, and here we've got our drag force. We can hit a point here where the drag force minus Fg here will equal ma, or Fd minus Fg, the balance of our forces, will equal ma for the object. Now, if the body falls long enough, this means its acceleration can cancel. When the acceleration downwards, the 9.8 meters per second from gravity, equals the drag force, then your acceleration ceases. We call this point terminal velocity. And to find the terminal velocity, you essentially set your accelerations to 0. You can substitute in for the drag force in these equations and say that 1/2 c rho a vt squared here, t being the terminal velocity, minus the force of gravity will equal 0. That means we can find the terminal velocity by twice the force of gravity, so 2Fg over c rho a rooted. It turns out for something like a skydiver that your terminal velocity is about 60 meters per second. Now the extra drag added by opening a parachute will take the terminal velocity to 5 meters per second. Very useful in stopping you hitting the ground and severely injuring yourself. Now the complication in these particular calculations, and why we didn't work it into any one of our varied problems, is because the drag coefficient is dependent on shape as well as the cross-sectional area. That means the drag coefficient for a sphere is 0.47. Half a sphere, 0.42. If we deal with a cone, it's 0.5, and as you can see, a cube is 1.05, but an angled cube is 0.8. So this is to do with how fluids will flow around an individual object. Long cylinders, 0.82, short cylinder, 1.15. So if we take the case of the cube, for instance, its drag coefficient is 1.05. It's also 0.8. That means if this object is tumbling, its drag coefficient is changing with time. making our life a little bit complicated, and meaning that we constantly have to find the area that's exposed to the fluid in our problem if we're to properly take this into account. So that would take a simple problem that we've looked at and make it significantly more complicated. Now, if you're to streamline a body, that means to shape it so that drag is reduced. We can see that our drag reduces immensely. So just going from a slab-sided cube here with a drag coefficient of 1.05, we can streamline something to 0.04 or half of it to 0.09. So this is something to keep in mind if you do intend to calculate your drag coefficients, and of course calculate such thing as terminal velocity, or indeed put air resistance into any one of your calculations. So in terms of terminal velocity, what we're really saying is this is the point where the drag force of the air, the fluid you're falling through, equals mg. In other words, the acceleration that's giving this force upwards as you fall through the air is equal to the acceleration of gravity. F is equal to mg. So as you can see from this graph here, this person is falling downwards. We'll let this complete. The only time this isn't equal is here. There we go. So quite quickly this person reaches terminal velocity. Now at terminal velocity, this often confuses people and they say, well, how is he falling? Remember, this is acceleration that is cancelled, not velocity. This would be wonderful if it was velocity that would cancelled, because as he reached terminal velocity, he would stand still in complete mid-air, which would mean we could have such things as cloud cities. But we can't do that. So this is acceleration that is cancelled, meaning at terminal velocity, he falls at one speed and no longer gains any more speed. So as a final summary, things to keep in mind. Your projectile is any object on which the force is only essentially gravity once it's fired. They'll travel with a parabolic trajectory when accelerated by gravity. No horizontal forces, only a velocity acting on our projectiles, so no horizontal acceleration after it's fired. The horizontal acceleration of the projectile is constant. Sorry, the horizontal velocity of the projectile is constant, and the vertical acceleration is by gravity. The horizontal motion of the projectile is independent of its vertical motion.